Alright, so in the last video, we cooked up a formula that allowed us to estimate the value along a function that was difficult to compute in terms of things that may have been easier to compute. Which is to say, our function value at x plus h was approximately our function value at x plus a small change in y plus a slope times a change in x, and f prime of x times an h. And when does this become useful? This becomes useful if we want to know our f of x plus h, but it's difficult to compute that, yet we're close to something that's easy to compute, and we're close to something whose derivative is easy to compute. Well then, as we did in this example before, was basically to say that the point that we're after along our function, we could just use the derivative to get the slope of the tangent line, and that's going to get us close enough. It's not going to be perfect, but it's going to be an estimate, and it's going to be an estimate that we can actually do, as we'll see, without even the need of a calculator. So here's an example. Use linear approximation to estimate the value of 2.02 to the third. Well, excuse me. Okay, frankly, I don't want to compute 2.02 raised to the third power. That's going to be a decimal times a decimal times a decimal. Like, that's going to get ugly, right? So, but, no, this is almost 2. So whenever you look at this and you think about it, what we're going to be thinking in our mind's eye here is that here is 2.02, and here is 2.0, or just 2, frankly. 2 and 2.02 are really close to each other. Our h is small. It's going to be real difficult to cube 2.02, so the thing that we want to know is difficult to compute. But the thing that's nearby is easy to compute, and frankly it's going to be easy to compute the derivative of this thing because this is just something cubed. So here's what we're going to do. We're going to consider the function y equals x cubed. And we are going to look at x equals 2 because we know what the function value at 2 is. That's just 2 cubed, which is 8. And we know what the derivative value at 2 is. The derivative value at 2 is just 3 times 2 squared. Because, we know the derivative would just be 3x squared. But 3 times 2 squared is 12. And moreover, we know what our h is. H is the difference between the point that we know and the point of interest. So whenever you look at your h here is just 2.02 minus 2, or 0.02. Okay, but now, if we know our function value, if we know its derivatives, if we know the change in the x's, we can use the slope of the tangent line with the change of the x to get the change in the y, to get the point along the blue tangent line function, which is almost the point of interest. And what does that mean here within the context of this problem? Well, using that formula above, we know that f of 2.02 is approximately equal to f of x, that's f of 2, 8, plus f prime of x, that's 12, times our h, 0.02. And what? When you take 12 times 0.02, I suppose that's not a wonderfully beautiful thing, but 12 times 0.02 is like 12 times 2 pennies, which is what, like 24 pennies? So 8 plus 24 pennies is 8.24. And now, here's the thing. Is 8.24 exactly the value of 2.02 cubed? No, it's not, because the function itself is a cubic function which is curved. The tangent line is straight, and a straight thing is not going to be exactly like the curved thing. But because our h is so small, there's only going to be so much of a deviation vertically. So much of a deviation between the value that we estimated and the value that you would actually get by computation. Because let me here run the computation on 2.02 times itself 3 times, 2.02 times 2.02 times 2.02. This came out to be, by direct computation, and it is 6 decimal places long and something I would not want to compute, frankly, by hand at all. The actual value came out to 8.242408. Look, we got pretty dang close. And that's sort of showing off the value of this technique. So the long story short is, if you want to compute something that is ugly to compute, but nearby to something that is simple to compute, use the computations related to the simple things to get yourself an estimate with only a small margin of error. And you do this by taking your known f of x plus your change in y, your slope times your change in x. And well, there you are. Let's do one more example after this to see this in action.